Um, so I'm here to introduce our work, which is called Informative Multimodal Unsupervised Image-to-Image Translation, or in short, InfoMUNIT. So my name is Tien, and other two authors of our work, Guillaume and Professor Blaise. So we all come from France. So the content of my presentation today includes introduction, some backgrounds about image-to-image translation, generative adversarial networks, and representation learning. And then I'm going to talk about our method, including the architecture, training losses, some results, and finally, I'll go to some conclusions. And from what I see from other presentations, I think we have pretty diverse backgrounds. So I will try my best to explain my work in the simplest way as possible. um, so before talking about our method, I just want to make sure that we all have the same idea on some terms. Firstly, let's talk about image-to-image translation. So it means translating images from a source domain to a target domain, and sometimes you can do backward as well. So for example, as you can see from the image here, you can translate from drawing to color images, or you can translate from real photos captured by cameras to some beautiful paintings. So the state of the art in this task, the state of the art methods now, they are convolutional neural network, and for training those models, there are two main approaches. They are supervised learning or unsupervised learning. So supervised learning, it means that we have samples in pairs. For example, here for each drawing, you have a color image. They are in pairs. But unsupervised training, you have no pair. For example, for photo, we have a bunch of photos and we have a bunch of paintings, but they are not paired at all. And actually, the second case is more popular in reality. So that's why we focus on this training setting. So now let's talk about multimodal unsupervised image-to-image translation. So as I mentioned in the previous slide, training with unpaired data, it's more popular. And when we do that, it means that one input image can be translated into multiple outputs. We have many possibilities. For example, if we translate an image of a cat we want to translate it into a dog, we have multiple options because we have a lot of types of dogs. So an unsupervised image-to-image translation model, it should be able to generate multiple outputs from a single input image. And many neural network architectures have been proposed for this task, but they have the same drawback, which is the lack of control on the features of the output. In other words, there's no relation among the outputs, so we have no control on the outputs. So in our work, we focus on disentangle these features. So one more thing to talk about, it is generative adversarial networks. So for anybody who works in the domain of image processing, I think you have already heard about generative adversarial networks, or GANs, and now they are applied in many other fields as well. So the rule is very simple. You have two networks in this system. You have a generator which takes random noise and generate fake images. And then we have the second network, which is a discriminator. It learns to distinguish between fake and real images coming from a dataset. So these two networks, they are trained in parallel. And after the training, both of them are very well trained, which means that the generator should be able to generate very real-looking images, while the discriminator can detect very well the fake images. Um, and that was the original generative adversarial network, the original GAN. And then we have InfoGAN, which is an extension of GAN. So here, the generator also learned to generate fake images, but here they add another network, a classifier, which learned to reconstruct the latent code. The latent code actually comes from the random noise, the input of the generator. So if the classifier is able to reconstruct that latent code, it means that the generator must learn to hide, to embed that latent code somewhere in the images, in the features of the images. So training the generator and the discriminator and this classifier makes the generator learn to embed, to learn to understand meaningful features of images. So at the end, by modifying the value of the latent code, we should be able to modify some meaningful features in the fake images, which we don't have in the previous slide in the original GAN. So why I talked about InfoGAN? Because we apply this principle in our network. So here we can visualize some example of what InfoGAN can do. So it learned to understand what are the difference between 0, 1, 2, 3 without giving any labels, or it learns a different between different levels of boldness, or the rotation of the images. So now let's talk about our method. We call it InfoMUNIT because it's a combination of two parts. The first part is multimodal unsupervised image-to-image translation, or MUNIT. It is another state-of-the-art, and we built our network based on this architecture. So this architecture enables us to translate images in an unsupervised manner. The second property of our network is learning meaningful features of images and also manipulating them. So as a result, our network should be able to translate images and able to control their features. And on the right, we have an overview of our network. So let's go slowly from here. So XA and XB, they are two images coming from two domains in our data set. So let's start at XA. So each XA is an image, and it is encoded by two encoders. One encodes the style of the image, and one encodes the content of the image. And then the original image is reconstructed by a generator. We take the style and the content as input. So this constructed image should look exactly the same as the original image. So that is the reconstructed training. And for translating an image from one domain to another domain, we firstly extract the content of the image, and then we give that content to the generator of the second domain with a random style code. So the domain here is the generator of the domain B. It takes the content of the image A. So it generates an image which has the content of the image A, but with a style look like coming from domain B. So that's how we translate one image from one domain to another domain. And also, as we can see here, we have a discriminator which learn to detect fake and real images. The presence of discriminator helps increase the quality of the generated image. And at the same time, it learned to reconstruct the information, the latent code, which is embedded into the style code. So the reconstructed information here must have a mutual information being maximized comparing to the latent code in the S that we found here. Yeah, so that's an overview of InfoMUNIT. And we also learn to reconstruct the content code. For example, here you can see CA going through the generator, and then we extract the content again. So this constructed content code should look similar to the original content code, and the same for the style code. It should look similar to the original one. So beside the architecture, we have a bunch of training losses. So as I explained before, here equation 1 and 2, we have the reconstructed loss for the image. And similarly, we have the reconstructed loss for the content. And then we have the reconstructed loss for the style. And beside, we have the adversarial loss, which help to improve the quality of the generated images in the equation 6 and 7. And then what we take from InfoGAN, it is that is the information, the mutual information. So here, as we said before, the mutual information between a style code and the generated image from that style code, from that latent code, should be high. So in our paper, we give more detail of how we handle technically this to maximize this mutual information. But in the scope of this presentation, we don't have enough time. So please take a look on the paper for the explanation in more detail of this transformation. And then in the equation number 10, we have the final training objective of InfoMUNIT, of our model, which is a combination of all the reconstructions loss, the adversarial loss, and at the same time maximizing the mutual information between the latent code and the generated image. we implement our experiments on multiple image-to-image translation tasks. For example, translation between edges and shoes, or edges and bags, cats and dogs, and painted to real portrait photos. And for the evaluation, we use conditional inception score and ellipse distance for the diversity of the generated images. And then for the quality of the images, we apply FID for the quality. And using those evaluation, we apply the same experiments on multiple baseline, which are the state of the art in the field: GAN, MUNIT, and RITS plus. So now let's take a look on some results. So as you can see, the objective of InfoMUNIT is to increase the diversity and the ability to control features of generated images compared to MUNIT and other state-of-the-art methods, at the same time not hurting their quality. So in this figure, we can see that the quality of images generated by InfoMUNIT are at least as good as the images generated by other methods. Especially if you look at the example on the right, GAN and RITS did not do the job very well for translating cats to dogs, but here we have MUNIT and InfoMUNIT did the job pretty well. And that result, the quality of the images, it's confirmed by this table. So here we, as I said before, we apply FID to evaluate the quality of the generated images. And as can be seen here, even though InfoMUNIT does not outperform other methods in terms of image quality in any task, its performance is stable across all the tasks. And in each line, we can see that the performance of our method is close to the best methods. So if we take a look at the average value, our method actually have the best performance. And then we evaluate our method and we compare it with other state-of-the-art in terms of image diversity. So on the left, we have the ellipse distance, and on the right, we have the conditional inception score. So we can also see that our method outperform the others in most of the tasks. We have done another test which show the advantage of our method over InfoMUNIT in terms of manipulating features. So in the figure to the left, we can observe that varying values of style code in MUNIT, this one, actually we can manipulate some small changes like the color of the object, but with our methods, we can significantly manipulate the features of the object. For example, the size of the bag or the color of the bag coming from light to dark. On the right, we can see the same, we can observe the same thing. The changes created by MUNIT is very small, but in InfoMUNIT, we can manipulate the feature in a very significant way. like the color and the style of the shoes. And yeah, and finally, it leads us to the conclusion. So in our paper, we propose a new method for multimodal image-to-image translation called InfoMUNIT as an extension of the state-of-the-art method MUNIT. And our method allows controlling the style of the generated images and improves their quality and diversity by learning to maximize the mutual information between the cycled and the distribution of the output images. And the method successfully explored and manipulate features of the output without any labels or annotation. Also, it achieves a superior diversity and competitive image quality compared to state-of-the-art methods in multiple image translation tasks. Yeah, and if you are interested to test our code, you can take a look on the GitHub that I put the link here. And I'm gonna update the code in this GitHub very soon. Thank you for your listening.
Thank you very much. The work is very interesting.
Thank you.
From forum.